Explain the working principle of a heat exchanger and common types. Heat exchangers work on the principle of heat transfer driven by the temperature difference between two fluids. The driving force is the temperature gradient, where heat flows from the hotter fluid to the colder one without direct mixing in most cases. There are two main types. Direct contact heat exchangers, where fluids come into direct contact to exchange heat, example, cooling towers. Indirect contact heat exchangers, where fluids are separated by a solid barrier, and heat is transferred across surfaces. In chemical plants, the most commonly used are shell and tube heat exchangers due to their high efficiency, easy maintenance, and ability to handle high pressures. I encountered them during my internship at Kribitko, especially in the urea production unit. I also saw plate-type heat exchangers used for applications requiring compact designs and higher heat transfer rates. What is the difference between a process flow diagram, PFD, and a piping and instrumentation diagram, PNID? A process flow diagram, PFD, is a schematic illustration that shows the overall chemical process, including major equipment, process flow streams, basic control loops, and key material balances. It gives a high-level view of how materials move through the plant and where major processes occur. A piping and instrumentation diagram, PNID, provides a much more detailed layout. It includes piping details, valves, control instruments, sensors, and safety devices, showing exactly how the plant will be controlled and operated. Both are crucial. PFDs are used for process understanding, initial design, and economic evaluation. PNIDs are used for plant operation, control system design, maintenance, and safety analysis. What happens inside a distillation column? What's the difference between tray and packed columns? A distillation column operates on the principle of relative volatility and boiling point differences. When a mixture is heated, the more volatile components vaporize preferentially. As vapor rises through the column and contacts descending liquid, mass and heat transfer occur, enabling the separation of components. There are two main types of distillation columns. Tray columns use devices like sieve trays, valve trays, or bubble cap trays to promote vapor-liquid contact in discrete stages. Packed columns use random or structured packing materials like Raskig rings or structured grids to enhance surface area for mass transfer. Tray columns are typically used in large-scale operations due to easier maintenance, while packed columns offer lower pressure drops and are efficient for vacuum or smaller capacity distillations. Explain the difference between laminar and turbulent flow. How do they affect pressure drop? Laminar and turbulent flows describe different flow regimes of a fluid. Laminar flow occurs when the Reynolds number is below 2000. The fluid flows in smooth, parallel layers with minimal mixing. Turbulent flow happens when the Reynolds number exceeds 4000, and the fluid experiences chaotic mixing and eddies. Impact on pressure drop. Laminar flow has lower frictional resistance, so the pressure drop across pipelines is low. In contrast, turbulent flow causes higher frictional losses, leading to a significantly higher pressure drop. When to prefer each? I would prefer laminar flow when energy efficiency is important, the system can tolerate slow transport, and minimal mixing is acceptable. I would prefer turbulent flow in processes where rapid mixing, heat transfer, or mass transfer are critical, such as in heat exchangers, reactors, or absorption columns. What is the difference between batch and continuous processes? When would you prefer one? In a batch process, feed materials are charged into the reactor, the reaction is carried out, and the product is withdrawn after completion. The system is closed during the reaction. In a continuous process, feed and product streams are continuously flowing, and the system operates without interruption. Selection depends on the application. Batch processes are preferred in industries like pharmaceuticals and specialty chemicals where flexibility, high-quality control, and small production volumes are needed. Continuous processes are preferred in industries like petroleum refining and fertilizers, where large-scale, high-throughput production is essential. Continuous processes are typically more economically efficient and offer higher productivity, but batch processes provide greater flexibility and control over product quality. What is a control valve and why is it important? Can you name a few types? A control valve is an automated device used to regulate the flow, pressure, or level of fluids in a chemical process. It is typically controlled remotely via a control system like a distributed control system, DCS, or a programmable logic controller, PLC, allowing quick adjustments based on real-time plant conditions. Control valves are critical because manual intervention is not always possible, especially in hazardous, high-pressure, or fast-changing environments. Common types of control valves include globe valves, commonly used for precise flow control. Ball valves, suitable for quick on-off operations. Butterfly valves, used for large flow capacities with low pressure drops. Needle valves, allow fine control over low flow rates. Diaphragm valves, often used for corrosive fluids. Each type is selected based on process requirements like pressure, flow rate, and fluid characteristics. Why are safety valves important? What's the difference between safety and relief valves? Safety valves are crucial devices in chemical plants that protect equipment and personnel by automatically relieving excess pressure to prevent accidents or equipment failure. I encountered pressure safety valves, PSVs, during my internship at Kribitko Fertilizers. They were installed on pipelines and pump discharge lines. When the system pressure exceeded a preset limit, the valve would quickly open to release the fluid, preventing overpressure damage. Difference between safety valve and relief valve. A safety valve is typically used for gases or vapors and opens fully and instantly when the set pressure is exceeded. A relief valve is often used for liquids and opens gradually, proportional to the overpressure. What are mass transfer operations? Name some mass transfer equipment used in chemical plants. Mass transfer operations are physical processes where mass is transferred from one phase to another or between different components in a mixture. They are essential in separating and purifying chemical products. Common mass transfer operations include distillation, separation based on boiling point differences. Absorption, gas is absorbed into a liquid phase. Stripping, removing volatile components from a liquid using gas. Leaching, extracting solutes from solids using a solvent. Adsorption, solute attaches to a solid surface. Drying, removing moisture from solids. Common mass transfer equipment includes distillation columns, absorbers, strippers, crystallizers, dryers. What is process optimization? Give an example from your experience. Process optimization involves improving process conditions to enhance efficiency, minimize energy consumption, reduce operational costs, or shorten processing time, all while maintaining product quality. It is crucial in chemical plants to improve profitability, increase safety margins, and reduce environmental impact. During my internship at XYZ Private Limited, I worked on optimizing reactor operations to reduce power consumption. I analyzed multiple parameters including impeller RPM, scale of agitation, baffle spacing, and length to diameter ratio. By carefully adjusting these process variables, I was able to recommend an optimal operating speed that significantly reduced power consumption while maintaining process stability and efficiency. What is a heat and mass balance, HMB? Why is it important in process design? A heat and mass balance, HMB, is a fundamental calculation in chemical process design. A mass balance ensures that the total mass entering a system equals the total mass leaving the system plus any accumulation or consumption due to chemical reactions. The general formula is input equals output plus accumulation plus generation/consumption. A heat balance involves balancing the total energy entering and leaving the system, usually based on enthalpy. It helps determine heating or cooling requirements to maintain process stability. Importance. Heat and mass balances are critical for designing equipment like reactors, heat exchangers, and separators. Optimizing process conditions. Ensuring safety and energy efficiency. Identifying material losses or inefficiencies in the system. What is a fluidized bed reactor? Mention one or two advantages. A fluidized bed reactor, FBR, is a type of reactor where solid particles, usually catalysts, are suspended and fluidized by an upward flow of gas or liquid, creating a fluid-like behavior of the solid bed. Advantages of fluidized bed reactors. Excellent heat and mass transfer due to high contact surface area. Uniform temperature distribution throughout the reactor, minimizing hot spots. Reduced reaction time and improved process efficiency, especially when using catalysts. Continuous operation and easy handling of solids. Applications. Fluidized bed reactors are widely used in combustion, gasification, catalytic cracking, and polymerization processes in industries like power generation and petrochemicals. What is corrosion? What are some types, and how can it be prevented? Corrosion is the chemical or electrochemical reaction between a material, typically a metal, and its environment, leading to material degradation and the formation of oxides or other compounds on the surface. Types of corrosion. Uniform corrosion, even material loss across the surface. Pitting corrosion, localized corrosion creating small pits, often leading to failure. Galvanic corrosion, occurs when two dissimilar metals are in electrical contact in a corrosive environment. Crevice corrosion, occurs in shielded areas where stagnant solutions accumulate. Stress corrosion cracking, caused by combined tensile stress and corrosive environment. Prevention methods. Applying protective coatings like paints or galvanization, zinc coating. Using sacrificial anodes, like magnesium strips on ship hulls, to attract corrosion. Selecting corrosion-resistant materials. Using cathodic protection systems. During ship maintenance, sacrificial magnesium strips are often used to protect steel hulls by preferentially corroding thereby extending the life of the structure. What is the difference between adsorption and absorption? Give one example of each. Absorption is a bulk phenomenon where one substance is uniformly taken into the volume of another substance. Example, absorption of carbon dioxide into an amine solution in gas treatment plants. Adsorption is a surface phenomenon where molecules adhere to the surface of a solid or liquid without entering the bulk. Example, adsorption of ammonia in the absorption towers I observed during my internship, where gases adhere to the solid adsorbent surface. A simple daily life example of absorption is water being absorbed by a sponge, where the water penetrates inside the sponge. What is the purpose of a cooling tower? Explain natural vs mechanical draft. In chemical plants, the primary purpose of a cooling tower is to remove excess heat from process water, usually coming from heat exchangers or reactors. The hot water is cooled by transferring heat to ambient air, and the cooled water is typically recycled back into the plant processes. During my internship at XYZ Fertilizers, I observed cooling towers with a capacity of 18,000 m superscript 3/h. These were induced draft mechanical cooling towers. Types of cooling towers. Mechanical draft cooling towers use fans to move air, enhancing heat transfer. Forced draft, the fan is located at the base, pushing air into the tower. Induced draft, the fan is located at the top, pulling air through the tower. This was the type I observed. Natural draft cooling towers use the chimney effect and natural air convection, without mechanical fans. Mechanical draft towers offer better control and efficiency, especially in large-scale continuous processes. What is a pump? What are common types and when are they used? A pump is a mechanical device used in chemical plants to transport fluids by converting electrical energy into hydraulic energy, enabling fluid movement through pipelines and systems. Main types of pumps. Dynamic pumps. Example, centrifugal pumps. Used for large flow rates at relatively low pressures. Common in general chemical plant fluid transport. Positive displacement pumps. Examples, reciprocating pumps, piston pumps. Deliver fixed volumes with each stroke and are used for high pressure, low flow applications or when handling viscous fluids. Selection criteria. For large flow rates and a variety of fluid properties, centrifugal pumps, single or multistage. For high pressure requirements, positive displacement pumps like reciprocating pumps. Pump selection depends on factors like fluid viscosity, required flow rate, pressure head, and system layout. What is the difference between a reactor and a separator? Give an example. A reactor is a vessel where chemical reactions are carried out under controlled conditions such as temperature, pressure, and residence time to convert raw materials into desired products. A separator is equipment used to physically separate components based on differences in phase, density, boiling point, or solubility. For example, in my internship at the urea production plant, ammonia and carbon dioxide were reacted in a high-pressure reactor to form urea. The reactor output contained urea along with unconverted ammonia and CO2. This mixture was then passed through a separator, which efficiently separated the unreacted gases from the urea solution, increasing the urea concentration. In short, reactor, where reaction occurs. Separator, where unconverted reactants or byproducts are separated to purify the product. What is process hazard analysis, FA? Why is it important in chemical plants? A process hazard analysis is a systematic and detailed approach used in chemical plants to identify, evaluate, and control potential hazards associated with processes that handle hazardous chemicals. Importance of FA. Helps prevent accidents, equipment failures, fires, and explosions. Protects human life, the environment, and plant assets. Ensures regulatory compliance and improves overall plant safety. Common FA methods. HAZOP, Hazard and Operability Study. What-if analysis. Fault tree analysis. Failure mode and effects analysis, FMEA. FA is typically performed during process design, before plant commissioning, or after significant process changes to ensure all potential risks are properly mitigated. What is the difference between a heat pump and a compressor? Give one use case of each. A compressor is a mechanical device that increases the pressure of gases by using electrical or mechanical energy. Compressors are widely used in chemical plants to transport gases or supply them at process-required pressures. For example, during my internship at Kribitko, compressors were used to compress CO2 gas before feeding it to the reactor. A heat pump is a device that transfers heat from a low-temperature source to a high-temperature sink using external energy, typically following a refrigeration cycle. Heat pumps are used in chemical plants for energy recovery and process heating or cooling to improve energy efficiency. Key difference. Compressors increase the pressure of gases. Heat pumps transfer heat between streams, often to save energy. What is the difference between a fixed bed reactor and a fluidized bed reactor? In a fixed bed reactor, solid catalyst particles are packed and remain stationary while reactants flow over them. An example is the ammonia synthesis reactor where gases pass over a fixed bed of iron catalyst. In a fluidized bed reactor, solid particles are suspended and fluidized by an upward flow of gas or liquid, creating a fluid-like behavior. Combustion and gasification processes often use fluidized bed reactors. In fluidized bed reactors, it's essential to achieve the minimum fluidization velocity, where the upward drag force balances the gravitational force on the particles, allowing them to remain suspended. Advantages: fixed bed reactor, simple design, easy to operate, and good for continuous processes. Fluidized bed reactor, excellent heat and mass transfer, uniform temperature distribution, and reduced reaction time. What is pressure drop? What causes it, and why is it important in plant design? Pressure drop refers to the reduction in fluid pressure as it flows through pipes, valves, fittings, and equipment in a chemical process system. Main causes of pressure drop: frictional losses along the pipe walls, elevation changes requiring additional head to move fluids vertically, bends, valves, fittings, and flow restrictions that create turbulence and resistance. Why it is important? Pressure drop must be carefully considered because it directly affects the energy consumption of pumps and compressors. Excessive pressure drop increases pumping costs and can lead to inefficient process operation or equipment failure if not properly accounted for. What is cavitation in pumps? Why does it happen and what are the consequences? Cavitation is a phenomenon that occurs in pumps when the suction pressure falls below the vapor pressure of the liquid, causing the liquid to vaporize and form vapor bubbles. As these bubbles travel through the pump and reach high pressure zones, they collapse violently, producing shock waves. Consequences: erosion and pitting of the pump impeller and casing, severe vibration and noise, potential pump failure or tripping, increased maintenance costs and operational hazards. Prevention: cavitation can be minimized by maintaining proper suction pressure, ensuring adequate net positive suction head, NPSH, avoiding excessive pump speeds, and reducing frictional losses in the suction line. What is the difference between evaporation and boiling? Give one example of each. Evaporation is a surface phenomenon where a liquid changes to vapor at temperatures below its boiling point. It occurs gradually and primarily at the surface. Boiling is a bulk phenomenon where vaporization occurs throughout the liquid at its boiling point, involving rapid bubble formation and vapor release. Example of evaporation: in chemical plants, multiple effect evaporators are used to reduce moisture content in slurries by evaporating water at sub-boiling temperatures under reduced pressure. Example of boiling: boiling is common in distillation columns and boiler systems, where liquids are heated to their boiling points to facilitate phase separation or steam generation. Both processes are essential in chemical industries, but they operate under different thermal and process conditions. What is the difference between a mixer and an agitator? Where are they used? A mixer is equipment designed to combine two or more substances to form a homogeneous mixture. It is typically used when different materials are introduced into a process, such as combining reactants or blending liquids. An agitator is used to maintain uniformity, enhance heat and mass transfer, or keep particles suspended within a single-phase system. It provides controlled movement of fluid without necessarily introducing new components. Key differences: mixer combines different substances. Agitator maintains consistency within a system, may involve only one substance. Example of mixer: used to mix reactants in a batch reactor or to blend additives in a continuous flow system. Example of agitator: used in storage tanks to keep slurry particles suspended and to ensure uniform temperature throughout the tank. Both are essential for achieving desired process performance. What is the difference between crystallization and precipitation? Give one example of each. Crystallization is the process where a dissolved solute comes out of a solution as crystals, typically due to reduced solubility caused by cooling, evaporation, or the addition of an anti-solvent. It is usually a controlled, slow process aimed at producing well-formed crystals. Precipitation is the formation of an insoluble solid from a chemical reaction or rapid change in solubility. It generally occurs quickly and may produce fine or amorphous particles. Examples: crystallization: in the sugar industry, sugar crystals are crystallized from mother liquor by controlled cooling. Precipitation: in pharmaceutical and specialty chemical processes, precipitation is used to remove unwanted ions or form solid products from solution. Both are essential solid-liquid separation processes in chemical plants but are fundamentally different in their driving mechanisms. What is distillation column reflux? Why is it important? In a distillation column, reflux refers to the portion of the condensed overhead vapor that is returned to the top of the column to maintain the internal liquid flow. This returning liquid enhances the contact between rising vapors and descending liquid, improving separation efficiency. Why reflux is important? It increases the purity of the top product. It improves mass transfer by providing a cooling and condensing interface. A higher reflux ratio reduces the number of theoretical trays needed but increases energy consumption. A lower reflux ratio requires more trays and may reduce separation efficiency. Reflux ratio. It is defined as the ratio of the reflux flow rate to the distillate product flow rate. Maintaining an appropriate reflux ratio is essential to balance product purity, column design, and energy costs. What is residence time in a reactor? Why is it important? Residence time is the average time that a fluid element or particle spends inside a chemical reactor. It is a key parameter in reactor design because it directly impacts the conversion, selectivity, and yield of the process. In ideal reactors like plug flow reactors, PFRs, all particles have nearly the same residence time. But in real systems, residence time distribution, RTD, analysis is used to measure how much variation exists in the actual residence times of fluid elements. Why it matters? Too short a residence time may lead to incomplete reaction. Too long may lead to overreaction or degradation. Wide RTD leads to poor control over product consistency. Accurate control of residence time ensures efficient use of reactor volume and predictable product quality. What is the difference between enthalpy and internal energy? Where are they used? Internal energy, U, is the total energy contained within a system due to the random motion, vibration, and interactions of molecules. It is a state function and forms the basis of many thermodynamic calculations, especially for closed systems. Enthalpy, H, is defined as H equals U plus PV. It represents the total heat content of the system and is particularly useful in open systems operating at constant pressure, like in heat exchangers and reactors. Usage. Internal energy is often used in first law of thermodynamics for closed systems. Enthalpy is commonly used in energy balances and flow processes, especially when calculating heat duties in distillation columns, evaporators, and heat exchangers. What is a pinch point in heat exchanger design? Why is it important? A pinch point in heat exchanger design is the location where the temperature difference between the hot and cold fluids is the smallest, also known as the minimum T. In energy integration, pinch analysis, the pinch point plays a critical role in determining the maximum possible heat recovery from process streams and minimum requirement for external utilities, like steam or cooling water. Why it matters? The closer the temperature profiles get at the pinch, the more sensitive the design becomes to heat exchange limitations. A smaller pinch, close to 0 degrees Celsius, can limit heat transfer efficiency and increase equipment size. A larger pinch improves driving force but may lead to higher utility usage and less heat recovery. Pinch analysis helps chemical engineers optimize the plant's energy use and design cost-effective heat exchanger networks. What is the difference between a CSTR and a PFR? When would you prefer each? A CSTR, continuous stirred tank reactor, is a reactor where the contents are continuously stirred to ensure uniform composition and temperature throughout. In contrast, a PFR, plug flow reactor, assumes fluid flows in plugs with no axial mixing, and the concentration and temperature vary along the reactor's length. Key differences. CSTR, complete mixing, uniform output, suitable for slow reactions or where temperature control is critical. PFR, no mixing along flow path, higher conversion per unit volume for positive order reactions. Selection. For positive order reactions, PFR is preferred as it offers higher conversion and efficiency. If the reaction requires intense mixing, heat removal, or constant composition, a CSTR is a better choice. In practice, multiple CSTRs in series can also be used to approximate PFR behavior when needed. What is a flash drum? How does it work, and where is it used? A flash drum is a vessel used to separate a liquid mixture into vapor and liquid phases by reducing the pressure suddenly. When a liquid at high pressure enters the drum and encounters a significantly lower pressure, the more volatile components immediately flash into vapor, while the less volatile components remain in the liquid phase. This operation is based on the principle that boiling point decreases with pressure, allowing partial vaporization at lower temperatures. Application example. At XYZ Fertilizers, I observed a flash separator used to increase the concentration of urea. The carbamide solution containing water, ammonia, and CO2 was passed into a flash drum. Upon pressure reduction, the volatile components vaporized and were removed, leaving a more concentrated urea solution. Flash drums are commonly used in distillation, gas dehydration, and urea recovery systems. What is the difference between thermoplastic and thermosetting polymers? Give one example of each. Thermoplastic polymers are materials that soften when heated and harden when cooled. This process is reversible and repeatable, allowing them to be reshaped multiple times. Their viscosity decreases with temperature, making them suitable for injection molding. Example. Polyethylene, PE, used in pipes and toys. Thermosetting polymers are materials that harden permanently when heated due to irreversible chemical cross-linking. Once set, They cannot be remelted or reshaped. Example: bakelite, used in electrical switches and sockets due to its high thermal resistance and rigidity. This distinction is critical when selecting materials for applications involving heat or mechanical reprocessing. What is fouling in heat exchangers? What causes it, and how can it be prevented? Fouling in heat exchangers refers to the accumulation of unwanted deposits such as salts, organic matter, corrosion products, or biological growth on the heat transfer surfaces. Causes: use of untreated or hard water containing calcium or magnesium ions, scaling. Entry of particulates or impurities into the process stream. Corrosion or biological growth under certain conditions. Consequences: reduced heat transfer efficiency due to thermal resistance. Increased pressure drop across the exchanger. Potential formation of hot spots, energy losses, and damage to equipment. Prevention methods: use of demineralized or treated water. Pretreatment of process fluids to remove contaminants. Periodic cleaning and maintenance schedules. Use of anti-fouling coatings or chemical inhibitors in certain systems. Controlling fouling is essential for maintaining efficient and safe plant operation. What is fluid compressibility? How does it affect compressors and pipeline systems? Fluid compressibility refers to how much a fluid's volume decreases under applied pressure. Gases are highly compressible, while liquids are nearly incompressible. In compressors, compressibility plays a critical role in gas compression. Compressible flow equations, like for isentropic compression, are used to calculate work input and pressure ratios. In pipelines, compressible flow, usually for gases, requires special consideration for pressure drop, velocity changes, and shock formation. In contrast, incompressible flow, liquids, uses simpler equations like Bernoulli's and Darcy-Weisbach. Ignoring compressibility effects in gas systems can lead to inaccurate designs, pressure surges, or equipment failure.